各位来宾，大家好！感谢各位嘉宾莅临美国国家科学院院长 Dr. Cicerone 的演讲。首先，我们请引言人国立台湾大学化学系教授彭旭明院士为我们引言。
Professor Cicerone, and good afternoon. On behalf of the National Taiwan University, I'd like to express my sincere welcome to all of you, and especially Professor Ralph Cicerone. And he came to Taiwan as the Academia Sinica lecturer. This lectureship was established in 2009 for celebrating the 80th anniversary of Academia Sinica. So every year we invited the Academia Sinica invited one or two lecturers to come to Taiwan and to give lecture. Yesterday, Professor Cicerone delivered a lecture at Academia Sinica. There are more than 600 audience come to participate the lecture. Today, he came to NTU to give second lecture on the title of Protecting the Ozone Layer was easier than stabilizing Earth's climate, economics, and politics. But before his lecture, I invited his good friend, Xiaochen Liu, for introducing Professor Cicerone. Please.
Ladies and gentlemen, good afternoon. It's a great pleasure and an honor to introduce my famous friend, Ralph Cicerone. As you can see here, Ralph is the president of the U.S. National Academy of Sciences. And with that position, he also chairs the U.S. National Research Council. His education, everyone can see it there. The information there, the hidden one is I heard that he spent more time on this rather than on that one. Nevertheless, he won a lot of important awards. Here, I just show you two of the most prominent ones. The first one is the 1999 Bauer Award. And of course, it was a prize. It's a big prize, lots of money. I went as a cheerleader, and even for cheerleader, they had me dressed in tuxedo. I still don't know how to put on the bow tie. The Franklin Institute, this award is a very important one. Many Nobel laureates got this award. In fact, the year before was C.N. Yang who got this award. And this award was for Ralph Cicerone's fundamental contributions to the understanding of greenhouse gases and also ozone depletion. In addition, I think actually more importantly, for Ralph's public policy leadership in protecting the global environment. And later on, when you hear Ralph's speech, you'll realize, you'll appreciate why they put there here. He always give great speeches. The other very prominent award, I think you can see by yourself, is Albert Einstein World Award that's given by the World Culture Council. In my opinion, his most outstanding seminal contributions are two parts. First is in 1974, his discovery of the chlorine catalytic cycle, which depletes stratospheric ozone, okay? And that paper was published even before Crutzen, Molina, and Rowland papers. And the other thing I think maybe even more important is he pioneered a lot of research activities on so-called non-CO2 greenhouse gases. These include, I think most of you are familiar with methane, N2O, CFC, and HCFC. These gases are much easier to control than CO2 itself. I asked him about, on my observation, why he's so successful, and I'm not. The first thing, obviously is not, I don't work as hard. The other thing I was interested that he's very curious about things, around what's happening and why. And I give you a good example as the concluding remark. I think I spent enough time. Here shows, here is our speaker today, Professor Cicerone, little Sarah, and we are near at a lake near their cabin. This is in 1976. Okay, that proof we were young ones too. It says here, listen everybody, this is not a simple fishing expedition. We have to heads up for any methane and N2O emission. And with that conclusion, I wanted to say one thing. 1976, he said this. In 1979, he worked hard on these things. He won the American Geophysical Union's Outstanding Young Scientist Macmillan Award, which is very difficult. He was 35 years, or maybe even 34 when he won that award. So here is today's speaker.
Thank you, Professor Peng, for the invitation to come here to Taipei. And thanks to my good friend, Dr. Liu, for that overly generous introduction. I would like to correct one error he made, and that is the recipe for success. That was not my response. That was his response when he won an Outstanding Alumnus Award from NTU. That was his recipe for success, not mine. Other than that, I thank you for the introduction. What I want to do today is to try to show the differences between two situations where humans are causing global environmental problems that can be very serious, and how we have dealt with them. And at the very end of the talk, I will make a direct comparison. Are we getting feedback? It's not the flowers. And we've turned off the other microphones, I think. that should be better now. And in one case, dealing with the threats to the stratospheric ozone layer, we've been very successful as a world with an international agreement that I will describe to you, and how very successful it has been, both in terms of the political agreements and in the actual results, which we can determine by measurements. But in the other case, the changing climate, while we have a strong amount of evidence from a scientific point of view, the countries of the world have not been able to agree on any adequate measures to provide incentives or regulations to control the situation. So this is a brief outline, and I won't talk about it too much, except, let's see, where's the button? I can't find the button for the laser pointer. The pointer.
Oh, that's a close.
Oh, I closed it, okay. Okay. No, I don't want this slide to, okay. So for the bulk of the time that I have with you today, I want to talk about the understanding of the ozone depletion and the human causes of the depletion of the stratospheric ozone layer and the actions, and then a similar discussion on climate change and human causes, and then finally a comparison of the two and what are the different ingredients and factors that have gone into them. So, as I said, we have these two cases where in the case of the Montreal Protocol, which is the international agreement to protect the ozone layer, it was preceded by a number of scientific assessments and international meetings which continue, and then leading to international agreements which are binding. That is, they have specific targets, specific goals, and requirements that nations have agreed to. In the case of climate change, we have had many international assessments, scientific assessments, the so-called International Intergovernmental Panel on Climate Change, IPCC, and many others, but no agreements. This is a blank. And that's basically the problem and the challenge. So let me begin with the ozone layer. Many of you have not heard about the ozone layer, and it's probably for good news, because the human threats have essentially been removed. But going back to about the time of that slide that Dr. Liu just showed in the early and mid-1970s, we had a lot to learn. We knew that, whoa, my goodness, sorry, excuse me. This is the, ozone is a layer in the atmosphere, above in the stratosphere, where there's a relatively high amount of ozone produced by natural causes. It's a part of nature, and that it has several important roles. First of all, it absorbs ultraviolet light coming from the sun. Ultraviolet light, which if it would reach the surface of the earth, could cause damage both to organisms and to property. And namely, that it had just been discovered in the early 1970s, late 1960s, that ultraviolet light breaks individual protein molecules, such as DNA, and it can cause certain diseases, especially in light-skinned humans. Basal cell carcinoma, squamous cell carcinoma, and some kinds of melanoma, skin cancers in humans. The absorption of that solar ultraviolet light also is a natural part of the movement of the atmosphere. It heats the upper atmosphere and causes some large-scale circulation patterns, and there was some concern before we knew very much that a large change to the ozone layer could change parts of the climate of the Earth too. And the temperature structure of the air would be very, very different. I'm sorry, I'm mishandling this. The temperature structure of the atmosphere would be very different without ozone. So I think what got people's attention, though, was partly this interaction of ultraviolet light with living tissue. So, for example, the sunburning response, when you get an inflammation of the skin from sunburning, erythemal response, it has an efficiency at these short wavelengths, which is quite high, and then as the wavelengths increase, this is ultraviolet light along here and going out to visible light over here. So when you buy sun repellent, like a cream that you put on the skin to protect the skin from sun, it's very effective in blocking these wavelengths of light, which would otherwise cause sunburns, and it extends, the efficiency extends out to here. Skin cancer has a wavelength response that's been mapped out largely with laboratory animals, but there's some epidemiological evidence as well that the skin cancer response also depends very strongly on these short ultraviolet wavelengths, and similarly with various kinds of suppression of the immune system. So there was medical concern and public health concern about any loss to the ozone layer, because if ozone absorbs ultraviolet light, which it does, and if you would reduce the amount of ozone in the natural atmosphere, then more ultraviolet light would penetrate. So we spent a lot of time doing calculations of how important this effect would be. This is just a cartoon to sketch it, different kinds of potential effects of ultraviolet B radiation, the middle wavelengths, due to ozone depletion. So we have the ozone molecules absorbing the solar ultraviolet, the sunlight, and you would have, for example, phytoplankton living in the surface waters of lakes and oceans, zooplankton, and then other fishery animals eating and surviving off of those phytoplankton and small zooplankton. That's just a cartoon to sketch the involvement of these aquatic ecosystems. Now, along came a group of chemicals that are not present in nature. These chemicals were synthesized by chemists in the laboratory to be ideal refrigerant fluids. When humans first invented refrigerators, the fluids that were used as the heat transfer agents were fairly dangerous chemicals. That is, if you breathe too much of them, you could become very sick. Ammonia, sulfur dioxide, somewhat corrosive. So these chemicals were built, synthesized, to be inert. That is, they don't react with anything. So, and they were ideal fluid transfer agents. Refrigerators could be designed very easily to cool something using these heat transfer agents, which would not harm the materials either because they were chemically inert. But by the late 1960s and early 1970s, they were so successful as a new industrial chemical that refrigeration, freezers, and air conditioners began to become common. So if you look around Taipei, if you look at buildings that were built before 1970, maybe before 1975, they don't have central air conditioning systems. It was just virtually impossible to build an efficient system then. Parts of the United States, like Florida, were not even settled very much. It was only after large-scale air conditioning and cooling was introduced to society that people could settle in hot, humid places, or else they were living very uncomfortably. Initially, these chemicals were used as refrigeration fluids in industrial systems, in freezers, in trucks to transport food, and in residences. Then they became popular as aerosol spray propellants. Just in the United States alone, the sale of aerosol spray cans reached something like 500 million or 1 billion per year at about $1 per can in 1970. So that was a multi-billion-dollar industry. Spray cans of hairspray, deodorants, cleaning products. There was even one spray can that was filled with 100%. There was no active ingredient except for the chlorofluorocarbon, and it was used to spray on martini glasses to make them cold. There were spray cans of catnip to give to your cat. They were very, very popular. At any rate, so the industry was growing like mad, And no one had bothered to figure out what happens to these chemicals when they're discharged from refrigerators or aerosol spray cans. And Mario Molina and Sherwood Rowland figured this out, that the chemicals are so inert that the only way that nature could destroy them would be after they drifted to very high altitudes above most of the ozone layer, say 30 kilometers above the Earth's surface. And then what happens? Well, as I say, it was a multi-billion-dollar market already in the 1970s, growing at 10% per year, and they were becoming more successful chemicals with more uses all the time, cleaning of electronic parts. The Japanese semiconductor industry had a requirement that their circuit boards had to be cleaned with this particular chemical, trichlorotrifluoroethane. There's a 2 missing there. That's an ethane series molecule. So they were very successful. They are essentially inert gases. They had been designed to be that way. But later, Molina and Rowland figured out that the catalytic chain which we had constructed with chlorine atoms could then be fed. That is, the chlorine atoms would be delivered from these inert chemicals on the surface of the Earth, but they would, as they went up into the stratosphere, they would start to encounter this same kind of ultraviolet light, which I've just mentioned, and that could tear the molecules apart, release chlorine atoms, and then the chlorine atoms could destroy ozone. Now, coincidentally, in 1975, there was a good friend of Dr. Liu's and mine named Ramanathan who discovered that these chemicals are also strong greenhouse gases. So that once released into the atmosphere, they would also affect the climate. Just very briefly, I want to sketch this out now. So this is kind of a structural diagram of what's called, which one is that? Trichlorofluoromethane. Three chlorines, 1, 2, 3, and 1 fluorine around a carbon atom. When they encounter this very, very short wavelength ultraviolet light, a chlorine atom is released plus an unstable remnant. But that takes very, very short wavelength ultraviolet light, which is simply not available on the surface of the Earth. So the theory was that this would be the only way that these chemicals could be destroyed by nature after they were produced by humans. And in the process, they would release chlorine atoms, which I will explain then goes ahead and destroys ozone. That so the theory had to be tested. And over the next few years, a great deal of research was done to test all these components of the theory. And eventually, this international agreement was put in place that they had to be banned, they had to be regulated. And I'll mention a few more things there. For those of you who are chemists, you will see fairly quickly that there's a catalytic cycle here. At the time, I was not enough of a chemist to even understand this. We had to discover it from the ground up without ever having heard of what catalysis was. But since then, I've learned a lot more chemistry. So the chlorine atom that I just mentioned is released, and it now can react with ozone to form a chlorine monoxide molecule plus a normal oxygen. Ozone is always being torn apart by visible sunlight to produce O2 plus an oxygen atom, and then in the third reaction, the chlorine monoxide, which is released in the first reaction, or produced in the first reaction, reacts with the oxygen atom to produce, again, a chlorine atom plus an oxygen molecule. The chlorine atom essentially replaces the one that was consumed in this first reaction, and if you ask what is the net effect, this is a cycle which destroys ozone with 1 photon of light and makes 3 oxygens. And this cycle can go on and on and on until something interrupts it. There are many industrial catalytic processes where a catalyst can be cycled 1,000,000 times or 100,000 times. And indeed, the calculation showed that every chlorine atom would reduce or destroy about 1/100,000 ozone molecules. So this was the basis of the concern that we had discovered, and also Molina and Rowland put it together with the very important chlorofluorocarbon problem, and that was the basis of the concern. But there were many things that had to be tested. All of these reactions, though, were based on what happens in the laboratory. We knew what we were doing, but in fact, there are some complications. In the air, when it's lit by sunlight, there are many, many other reactions going on simultaneously. So a more complete reaction scheme had to consider nitrogen dioxide reacting with the CLO and many, many other reactions, hundreds of them, which I won't show you any more of, but all of these things had to be discussed. So now, the Montreal Protocol. By 1987, 13 years later, there was a meeting in Montreal, which was the third or fourth such worldwide meeting, where it was proposed that these chemicals should be regulated. And it was an ingenious agreement, very sensible. So I think more than 50 nations signed almost immediately, and it went into effect in January of 1989. The provisions of this agreement were to phase out the production and consumption of the same chlorofluorocarbon gases that I mentioned earlier, plus several others that were completely halogenated methane and ethane series compounds. They were to be, worldwide law was that no country could produce or consume more of these chemicals than they had done several years earlier. So it was a beginning of a phase out. But they provided in this agreement something that's very important for these complicated problems. They provided that there should be reviews of all the information every 2 or 3 or 4 years. So that, for example, if on the first review some flaw had been found in this proposal, which we had been working on for 13 years worldwide, but it was still possible that there would be a flaw, the agreement could be relaxed, and that the chemical companies could go on producing these compounds longer. On the other hand, if the review would show by international agreement that the problem was worse than had been originally predicted, that we would lose more ozone, or that there would be more human health effects or more climatic change than we had expected, then they could tighten the agreement to make the production and consumption of these chemicals less approvable. And indeed, the Montreal Protocol was reviewed in 1991, 1993, 1995, 97, 99, and it continues today. It's now signed by 190 nations around the world, and also by the European Union as an agreement internal to the European nations. And now, the complete banning on these chemicals has been agreed to. Complete removal, no more production, no more usage, no more sales, no more distribution. And the class of chemicals now includes a wider variety of chemicals than was originally saw. It includes a number of chlorocarbons which are not totally halogenated, used for many other purposes. Some compounds containing bromine, because the bromine released into the stratosphere has also been proven to consume and deplete ozone. And even some of the replacement compounds, which are hydrogenated chlorofluorocarbons, which are now our current refrigeration fluids for the most part. So this agreement was approved internationally by more and more nations, and every time it was reviewed, it was made more strict, tougher. The exclusions were reduced. The numbers of chemicals that were allowed to be produced have been decreased. And I'm going to show you just a few results of what's happened. But just a few of the ingredients that went in. First of all, the protocol was preceded. That is, what happened in Montreal in September of 1987 was preceded by a number of international scientific assessments and intergovernmental meetings. The protocol was enacted, importantly, before there was any evidence of actual harm to humans or any living creature, the biota. when this protocol was enacted, there was no evidence of any actual harm. In 1990 or 91, there was one paper that I remember seeing that had some evidence that some surface-living phytoplankton, that their productivity was decreased when they drifted under the ozone hole, which I'll describe next. But that came later. Furthermore, this entire protocol was enacted before the Antarctic ozone hole was shown to be due to these same chemical reactions. And this is very interesting to realize. There are several books that have been written about this whole process of the discovery, the international negotiations, and what the politics and the economics are, who was fighting for the protocol, who was against it, and so forth. This book was written by a reporter named Lydia Dotto, who worked with a Toronto, Canada newspaper, and a friend of Shaw's and mine, who was a chemist. This book was written by the diplomat who led the international negotiations. It's called Ozone Diplomacy. There was another book by a journalist named Sherry Rowan, another book by a political scientist named Parson. So many people have looked back at the Montreal Protocol, and they continue to do so. I saw an article in the Wall Street Journal about 3 weeks ago about how successful the Montreal Protocol has been, that people have been writing books about the subject, about why this has worked so well. So let me give you just a couple of more tidbits of the science. The Antarctic ozone hole was a sudden discovery that no one had predicted. Namely, in 1985, the British Antarctic Survey had been doing measurements at the South Pole for meteorology and geology purposes. And by looking up at the sun and measuring the ultraviolet light carefully, they were able to infer how much ozone was in between the surface and the sun. And they discovered that every year in the August and September and October, the ozone was going down to very, very low levels. So they finally reported the result. It was as if there was a hole in the ozone layer overhead, and within a year, their results were confirmed by satellite observations of instruments looking down at the Earth. And they said that the depletion of ozone was so large they could have seen this from Mars. So that it was a big phenomenon. It was not predicted. It was not understood. It was a very large loss of ozone over Antarctica. And the biological damage that I mentioned to you was discovered by shipboard oceanographers who were doing phytoplankton surveys in the southern oceans not too far from Antarctica. And they found that on certain days when they were under the ozone hole, the phytoplankton productivity and the rebirth of phytoplankton was greatly depressed. The ultraviolet light was hurting them. It was an annual event from the time the sun comes up over Antarctica. That's the end of their winter season and going into the spring. The sun comes up at the end of August. As soon as the sun comes up, the ozone would essentially disappear, and it would last until December every year. And the fact that these ozone losses were caused by chlorine and then bromine was established around 1989, 2 years after the protocol was enacted. So our friend Sherry Rowland, who died a couple of years ago, had a collection of cartoons that showed what the public reaction was in many ways, and this was expressing the element of surprise of the ozone hole that was being observed, that the sun will come out tomorrow and then she would be fried in the ultraviolet light. So the mechanism was shown to be a little bit of a variation on the one that I showed earlier, where in the normal atmosphere, the chlorine atoms can be taken away by being converted into hydrogen chloride. And what was shown after some investigation in aircraft and balloons in Antarctica, and then some laboratory studies, was there was a what chemists would call a heterogeneous reaction. Not just gases reacting with each other, but gases reacting on solid surfaces, which could form because the Antarctic stratosphere is so cold that matter can condense on just a tiny amount of water vapor and some nitric acid, and so that the hydrogen atom binding the chlorine atom, the chlorine in this way could be converted into diatomic chlorine, which is then easily liberated in visible sunlight, and the ozone destruction had a more complicated cycle to it, which is actually square law in the amount of chlorine. So this reaction can go very quickly, the same kind of net destruction. And the fact that this was shown so quickly, like 18 months after the discovery or 2 years after the discovery of the ozone hole, was quite impressive. And a lot of people, meteorologists and chemists, deserve a great deal of credit. But the bottom line from a regulatory point of view is that there was a kind of a smoking gun, that is, a single piece of evidence could show what was happening, and that was the simultaneous measurement of the ClO molecule and ozone. If you write down the kinetic equations, you can convince yourself that if you could measure ClO and ozone together, you could essentially prove this mechanism. In fact, the DuPont Chemical Company testified to this idea in 1974 in the United States Congress. I was present. I was one of the other witnesses. And the DuPont representative said that they had also concluded that a simultaneous measurement of ClO and ozone would be the smoking gun proof that all of our mechanisms were correct. And indeed, this is a depiction, obviously just a cartoon, of the Antarctica down here above, and this region above in the high atmosphere where the winds were swirling in such a way that the vortex sealed off that part of the atmosphere from everything outside. So if you could start, for example, destroying ozone inside this core, there was really no way to regenerate it by air coming in from the outside. The only way to regenerate the ozone would be the fairly slow natural production from sunlight. And indeed, that's what was shown. This is a beautiful piece of work from a friend of Dr. Liu and mine, Jim Anderson. So before the sun arose over Antarctica in the third week of August, there is a normal amount of ozone, this red curve, graphed versus latitude. This is a high southern latitude going towards the South Pole, and the normal amounts of ozone were seen in this red curve. Then after the sunlight came up and the ClO concentration rose, as you go towards the pole, the ozone amounts were reduced by about a factor of, 5, and so forth. And these results were reproducible and shown to be true all the time. So the evidence was really in hand. So when the Montreal Protocol revision was considered, it was made stronger every time because more evidence like this was coming in. Ozone layer was being decreased around the entire globe, not just Antarctica, although much less, so that the amount of biological damage was never very large. Now, something happened about 3 or 4 years ago that this is a group that, and this paper, let's see, our friend Yuan Li was involved in one of these papers, but the point is some people here in Taipei did some fabulous work because an idea had come up that one of the chemical reactions that I just illustrated should have another branch to it. And if you looked at the consequences of that branch, that reaction pathway, there would be much reduced attack on ozone, and this mechanism would not be so important, and maybe the theory was not right. But through some ingenious laboratory experiments, this group involving Yuan Li and then later independent groups were able to show that the reaction pathway, which I just speculated on, was not important, and the main pathway was what I had shown earlier. So this is typical of what the scientists have been doing over the years. They keep trying to find any mistake and doing better and better, And the original theory has really held, so that the basis of the Montreal Protocol has become stronger and stronger over the years, and the international negotiators have made the agreement stronger. Some of the other evidence that it has worked is that if you go back, 20 years, the concentration of this chlorofluorocarbon measured versus time, it was still going up at this rapid rate because the CFCs were being consumed and used and produced so much faster. But after the protocol and the limitations were put into place, the concentration of this particular chlorofluorocarbon has gone down with time. The same with this very inert one and this very inert one. So the protocol has been very successful, and indeed the ozone layer has begun to heal all around the world. The Antarctic ozone hole continues to happen every year, and it will probably continue for another 50 or 60 years because it takes that long for sunlight to remove these molecules completely. Wait, I said that wrong. This graph, what did I do? I just killed it. I just jumped all the way back. Excuse me, something's happened here. I'll get there. There are too many buttons on this controller, and my thumb is too big. I'm sorry. This graph that I just showed you is actually the emissions, that is the tonnage emitted every year. So the chemicals were being emitted into the atmosphere at a peak level until about 1989 when the protocol went into effect. And the emissions measured in so many million tons per year have decreased. This one has decreased almost to zero because other chemical substitutes were found. And then if you actually go out and measure what's in the atmosphere, these are the measured concentrations of those same chemicals also decreasing very rapidly. Not so rapidly because their lifetime in the atmosphere, the rate at which the atmosphere destroys them, is fairly slow, but they are certainly going down now. And that is proof that the behavior and the compliance to the treaty, because of provisions built into the Montreal Protocol, the compliance has been good. Not perfect, but good. Now let's talk about climate change, at least briefly. There is a series of these international assessments which I know people here have contributed to, and everyone hears about them in the newspapers every few years. The Intergovernmental Panel on Climate Change is a very high quality assessment. In 2007, we heard about some errors that were present in the 2007 assessment, but they were relatively minor. Hundreds and perhaps 1,000 scientists work on these every few years. So the latest one was released in September of 2013. It has about 1,200 pages in it, peer-reviewed literature about the physical science basis of climate change and what are the current estimates of how well we understand it all. So there are many assessments, and I'll just show you a little bit of the evidence that climate change is happening. Some of you are very well aware of these results. These are actually a depiction of temperature measurements around the Earth that you can interpret as a global average by doing the appropriate geometry and weighting, where 0 on this graph is not 0 degrees temperature, but it's a reference level. And it happens to be the 30-year average of all the temperatures measured all around the Earth between 1950 and 1980. So anything that's below 0 is a lower temperature, a global average temperature, and everything above 0 on this graph is a higher temperature, up about 1 degree Fahrenheit or about 0.6 degree centigrade in this time period. And it shows, of course, some structure and some statistical uncertainty shown by the green bars, but generally a warming since about 1979 or 80 to the present, with a decrease in the rate of warming in these years. But you can see there have been years when there have been large excursions up and down, generally continuing going up. And we won't talk about this history right now, although it's very interesting. This is a depiction of the same data, but taking everything north of the equator in the red ink and everything south of the equator in the blue ink, showing that there's more warming in the northern hemisphere than in the south. That's probably partly due to the fact that the southern hemisphere has twice as much water in it as the northern hemisphere does, so if you put some external influence causing a warming of the Earth, you're going to see a faster warming where there is more land and less ocean. So this all hangs together. There's much, much evidence that I won't go through now, including some geographical. This is obviously a two-dimensional map of the Earth with the equator going across the middle. The Arctic up here showing very rapid warming. There's a false color chart of temperatures here. So very big warming compared to the 1960s reference time here, here. These are just 4 sample years. 2014, the first 2 months. 2010, the first 2 months. 2005, the first 2 months, compared to all. Obviously, you can do this graph every month. So in about a month, we'll be able to put the point for March on this graph just to see what the breakdown is with every month of the year. So the data have been aggregated, they've been separated month by month, they've been separated into geographical regions to make sure we understand what's happening. And then the same with the oceans. The temperature of ocean water is not measured as well as that of the atmosphere, because in the atmosphere we have more meteorological stations in many cities. We have aircraft, commercial aircraft making measurements, whereas with the ocean, there is not as much sampling. But it's now been shown that the heat content of the oceans has increased over, this happens to be about the 55-year period. The world ocean is in black ink, showing that the ocean heat current has increased this amount. It's about 6 times 10 to the 22nd joules in the world oceans, and then different amounts in different ocean basins. Let me come back to this one now. Another important climate variable that has been measured extremely well now is the total amount of ice that's sitting on the Greenland continent and the Antarctic continent. This one happens to be Greenland, and over the last 10-year period, which is the only period for which these data exist in a quantitative way, shows a loss of ice of about 260 billion tons per year with an acceleration rate that is, this is not a straight line, it's a downward-facing parabola, which shows an accelerating loss of ice at about 28 billion tons per year. And the same for, this just shows a rapid loss in that 1 year. I put a circle around it where I can't get the next one to come back. There it is, Antarctica. The data are noisier because the behavior of the Antarctic ice is somewhat different from west to east. So some years the accumulation in one half of Antarctica is fairly large, and the melting on the other one doesn't compensate as much. But generally speaking, there's a decrease measured now over 10 years on the Antarctic continent. And the important part of this ice is that when it is lost, it raises sea level. If we simply melt the floating ice in the ocean, of course, it does not raise sea level. So that's why this ice is important, and I wanted to mention it. One more thing that I'll just mention briefly is sea level. Sea level is now measured very, very well by Earth-orbiting satellites with ranging instruments on them, LIDAR, as well as an interferometric synthetic aperture radar measurement. And it shows that sea level increase during the time that it's been measured, about 21 years now, has risen along this linear trend, although there are some very interesting excursions up and down at about 3 millimeters per year, which is about twice as fast as had been measured before the satellite era. So there really is evidence of climate change, and the last piece of data I'll show you are measurements of the energy coming out of the sun reaching the Earth, which in the last 30 years, this quantity has been measured for the first time accurately enough and precisely enough to make this comparison, which shows a more or less cyclical behavior of the visible and near-infrared light coming to the Earth from the sun. And what this means is that the changes that I just showed you over the last 20 or 30 years, including the temperature data, that these are not happening because of a change in the sun. It looks much, much more like a human influence, which we have concluded is almost certainly, these changes are almost certainly due to humans and not due to the sun. And one of the underlying causes, of course, is the observed increase in carbon dioxide, a principal greenhouse gas measured since the late 1950s into this year, not only at Mauna Loa, but at about 30 other sites around the world, and satellite measurements. And I'll just mention briefly some of the evidence that this carbon dioxide is coming from human fossil fuel burning for the most part. Although, as Dr. Liu mentioned, there are other greenhouse gases, and others have a different story, but mostly human causes. I'm going to skip over this because it's not essential to the argument. But one of the beautiful pieces of research that came available in the late 1980s was the measurement of carbon dioxide and methane amounts trapped in polar ice. Several countries in the world, I think led by the French and the Swiss and the Danes and the Russians, have found ways to drill down into these very deep ice layers on Greenland and Antarctica and then extract cylindrical cylinders of ice, and then to chop and slice the ice and even to crush it in some cases, to do age dating on how old the cylinder is. And the deeper you go into the ice, the older the ice is, and then to extract the gases that are trapped in that ice. So when you do that, when they do that, they create these age distributions of the methane and CO2 in ice. So here we are at time zero, which is now, or sometime in the 20th century, going back 50,000 years, 100,000 years, 200,000 years, and so forth on both charts. And we know that there have been ice ages on the planet. So for example, 20,000 years ago, we had the last significant ice age. And when it was very cold, and the way to determine that is some isotopic contents of the ice, the water. When it was cold, the carbon dioxide amount was about 175, 180 parts per million. You can see the number here. And when it was warm, like at the beginning of the industrial age, around the year 1800 or so, the amount of carbon dioxide was about 270 or 280 parts per million. Cold, 180, warm, 280, that's 125,000 years ago, 120,000 years ago. When it was cold, 145,000 years ago, CO2 would go back down to its low level. But CO2 over the last 4 planetary ice ages would vary between 180 parts per million and 280 parts per million. But now what's measured is nearly 400 parts per million. So whatever is going on, whatever is causing this increase, has never happened before in the last 4 planetary ice ages. So it begins to look unnatural. And it's the same with methane, and it's the same with several other greenhouse gases. Again, from the point of view now of should humans take this seriously? Should we try to limit these future increases of carbon dioxide? Well, if we have a lot of scientific research to do, but the evidence continues to mount that the changes are due to humans and that they are going to cause even more significant climate change as we go along. And some of the pieces of evidence that the carbon dioxide is from fossil fuels is that the time history of the CO2 increase and that of fossil fuel usage, they match each other very well. We're using about 150 times more fossil fuel now than we did 100 years ago, with much of the increase just in the last 30 years. The amounts of the CO2 increase that we're measuring in the air they match the fossil fuel emissions within about 40%. So they're not perfect, but they're close. I have already compared what's in the air now compared to the last 4 glacial cycles. It's unnatural. There are geographical patterns of the atmospheric CO2 which also match the human emissions. The isotopic contents of the carbon dioxide, especially the carbon-12, carbon-13 ratios that we see in the atmosphere now, match that of fossil fuel, and they don't match other patterns. And then there's another very important set of observations which I won't go into today, but there is actually good data now showing that the amount of oxygen in air is decreasing by a small amount, but it matches the amount very closely to the oxygen consumption by fossil fuel burning. That is, the making of CO2 from fossil fuels consumes oxygen. So there's all kinds of evidence that this change is from human usage. And I'm rushing because I want to get to this last point now where we make some comparisons. Let's just start one by one and look at the difference in what humans have agreed to do and what they've been capable of doing for these two global issues for which there's really strong scientific evidence that things are changing. First of all, this is an observation which is perhaps my opinion, not so much evidence, but the framing of the issue from a public point of view. Those of you who think about political science and maybe opinion surveys and so forth, quite often when climate change is discussed, it's put in terms of politics and government action. For example, regulatory events. So the framing is as a political question rather than a scientific one. In the case of the ozone depletion, the issue was framed for many, many years as a scientific one. And it was emphasized as being scientific, for example, when the ozone hole was discovered. It was a discovery. We didn't anticipate it. And it was quite evident that it had nothing to do with politics or money. It was a discovery of a phenomenon that had occurred. So I think an important framing issue here in terms of public attitudes has been that the ozone layer was thought of very strongly as a scientific issue alone, whereas climate change, as soon as the discussion starts to, is this real or not, many people like to think that it's not because the actions to reverse it would be very painful, for example, or that money is involved. Secondly, in the case of, can we test this theory? Well, in the case of the ozone layer depletion, it had been recognized very early on, as I say, and confirmed by the DuPont company, which was the largest producer of chlorofluorocarbon chemicals. It was a multi-billion-dollar industry. They agreed in 1974 that there was a simple and compelling test to test the whole theory. And that test turned out to be confirming when Anderson and other colleagues began to measure chlorine monoxide and ozone amounts together at the same time in the same parcel of air. With climate change, I think to test this entire theory that humans are causing global climate change, not only with greenhouse gases, but with emissions of soot and black carbon and a number of other things, maybe even by changing cloud patterns. The test is going to be less, it is already less direct. More variables are involved. In fact, I've shown you some of the variables today that we're trying to cover to see if we're understanding everything. The temperatures of air, the temperatures of water, the amounts of ice, sea level rise. And as Professor Hsu pointed out the other day, there's another test, and that is the temperature of air as you go above the surface of the Earth. It should actually get cooler with time. And that test, by the way, has been confirmed as well. But the point is that the tests of the theory to convince everybody are not as direct, and they involve more variables, sometimes simultaneously, sometimes with time lags. So it's more complicated. Health effects. In the case of ozone, there were very, very real threats of increased rates of skin cancer, including the most dangerous kinds of skin cancer. Not quite as clear as the medium grade skin cancer, but during the entire years, that 15 and 20 years that this discussion went on, skin cancer was almost always at the top of the list of people, especially light-skinned people, Caucasians and many Orientals. Skin cancer was at the top of the list of concerns. With climate change, at least yet, there are much more indirect thoughts about what will be the health effects of climate change. I mean, for example, there are some logical, plausible ideas, such as areas that will become warmer with more moisture and stagnant water. There might be more mosquitoes and mosquito-borne diseases and certain kinds of water-dwelling viruses. It's logical and it's plausible, but it's much less direct, and the evidence is not so clear yet. We don't have enough evidence, in my opinion. If there's a public health expert here who disagrees, I hope that you will speak up. Complexity. The entire situation, looking back on the ozone layer, it looked very complicated at the time, especially to someone like me. I was learning chemistry as I went along. My colleague Richard Stolarski, who worked with me, when he heard about the structure of these chemicals, he said, "Oh, that's too complicated. We'll never understand it." But of course, now we realize these are simple molecules compared to what we thought then. And the argument was, whatever is happening, it's probably happening over a good part of the entire world, the original thoughts. Whereas with climate change, we have natural historical climate changes going on all the time. We have strong evidence of regional climate changes that have happened during the time of humans, like the Little Ice Age in Europe, the medieval warm period, where large regional changes in climate, global climate changes. There are other things that cause climate change. And the orbital parameters of the Earth going around the sun, the so-called Milankovitch cycles and the wobbles of the Earth and so forth, these things cause climate changes. We know that they will continue. So what we are doing as humans is superimposing changes on changes which are already occurring. The situation is more complicated. Now, we think we've seen the human signal emerge. That is, and if you read the IPCC assessments, for example, the conclusion is that the evidence is strong that we are seeing human-caused climate change already, and it's really just beginning. But there are also local differences. For example, the warming of the Arctic that's been seen is about twice as much as anybody could have predicted. Is that right? About twice as much? So there are local differences. And another important thing in climate change is we have the involvement of living systems. And what I mean by that is there are feedback processes, some of which involve living systems like microbes that live in the soils. They will behave very differently if the soil is wet or very dry, and they will behave very differently if it's frozen as opposed to melted water. And those have important feedbacks. The greening of the biosphere, as we add more carbon dioxide to the air, there are different photosynthetic mechanisms, for example, C3 and C4, but there is increased growth in some green matter due to increased carbon dioxide, which then creates a feedback on the system. So there are all these complications. Here's an interesting one. Who's guilty? In the case of the chlorofluorocarbons, the chemicals were totally synthetic. We knew who was producing them. there were really only 6 companies in the entire world who were producing almost all of the chlorofluorocarbons. So if we ask, some people thought, well, we can point the finger at the guilty parties, and they could name the 6 chemical companies as if they were causing all of the problem. But with climate change, every person in the world who's using fossil fuels, 7 billion people and many nations, past and future emitters, have to share the blame, so to speak. So we can look in the mirror every time we drive an automobile fueled by gasoline and so forth. We have to realize that we're part of the problem. So the point is, in dealing with this issue, we cannot simply point the finger at a few chemical companies and say, all we have to do is put you out of business and we've solved the problem. It's much more complicated. For example, the differences between the nations that are very advanced, and I'll give you just 2 examples, the United States and Canada, who have burnt fuels for, let's say, 100 years and loaded the atmosphere with carbon dioxide, but they are no longer the biggest emitters. They have been passed by China, mainland China, in the last few years. So bargaining, so to speak, and getting nations to accept the proper share of their responsibility, you get a different answer if you look back in time and say, well, the United States has caused most of the problem. But if you look ahead in time now, you see the industrial development of other parts of the world going so fast that the future loading of the atmosphere is due to what they are doing, primarily. So I'm exaggerating for the case of simplicity, but this issue of saying, well, whose interests have to be protected here, and who can help in creating a solution, it's very different between the ozone layer, with which we dealt quite successfully, and what we've been able to do so far for climate change. Although, once again, other processes are involved in addition to fossil fuel burning, but this really is the dominant one. So that's why I'm simplifying. There's a few more. One is the need. An economist would think in terms of commodities for which there are substitutes. For example, if you don't like polyurethane foam coffee cups or teacups, you can replace them with paper. Or you could use porcelain, pottery, and so forth. In the case of the chlorofluorocarbons, first of all, the usage as aerosols, people knew that they did not need these compounds. In fact, the producers of aerosol spray cans were doing an enormous amount of advertising to convince consumers that if they wanted a hairspray, they should throw away the one that you would pump with your fingers and use their aerosol spray products instead. And with underarm deodorants, the advertising money was enormous to try to convince people to use those products. So the consumer already knew that he or she had a substitute. They didn't even need the aerosols. So this, from an economic substitution point of view, that one was easy. Then the chemical companies themselves, including DuPont, produced substitutions for these CFCs which were much safer to the ozone layer, simply by changing the chemical synthesis to, and I won't go into the details, but the point is there were substitutes available for air conditioning units, for freezers, for automobile air conditioners, for home air conditioners, etc. Now look at fossil fuels. What substitutions do we have for heating, producing electricity, and transportation? Well, for transportation, we're not doing very well. We don't have electric cars yet to speak of. Almost all the transportation in the world is being energized by hydrocarbon liquid fuels. And there's a good thermodynamic reason for that. They carry a great deal of energy per unit volume, and from a chemical point of view, they don't carry the oxidizer. The oxidizer is the oxygen out of the air, which comes for free. So when you fill up your gas tank, you do not have to fill it with an oxidizer to fuel the combustion. it's already in the air. So you've got a big advantage over using hydrocarbon fuels. So it's going to be very difficult to substitute for fossil fuels, both for heating, creating lighting and electricity, and transportation. But what are the substitutes? Well, renewable energies, and this is the long-term goal, and it is possible, but we need better energy storage to permit wind energy and solar energy to be more or less stable over the course of a day or a season to satisfy the so-called base demand for electricity. So from a point of view of substitutes, there's also a difference, and these are real problems. These are science and engineering problems, and not just a question of preference or values. And that gets into the same thing. I'm really just duplicating what I said. But there were substitutes available for the chlorofluorocarbons. They took a little bit of development, but they've turned out to be very successful and safe. But for the energy needs that the world has, we have renewable energy, we have nuclear power, but not yet to the scale that's needed. We are not supplying a very large fraction of our electricity from either solar or wind yet, although some countries like France are supplying 75% of their electricity from nuclear power. Most other countries have not even come close because we have to deal not only issues of safety, but also in waste handling, waste reprocessing, preventing the waste nuclear materials from being used to create fissionable material for bombs as well as dirty radioactivity. So there are substitutes available, but we haven't achieved them yet to the extent that we need. The international assessments, yes, we've had an enormous number of successful assessments about stratospheric ozone, with scientists around the world agreeing. It took some years before that happened. The measurements that were made by scientists in one country had to be more or less accepted. I mean, for example, when the ozone hole was discovered by the British, the American scientists who had the satellites capable of making the same measurements had been asleep at the switch. They missed it. But on the other hand, the original discovery of the action, the British were a little bit resentful because they hadn't made the discovery, and they were slow to accept the results from other scientists, and that's the way we work. But the point is, the assessments are now so well accepted internationally that they've resulted in a tightening of the Montreal Protocol to the point that we can now see its success, and these books are being written. Everybody's trying to understand why these things have been so successful for ozone. But in the case of climate change, the quality of the assessments, I think, has been very high. They have a little more government participation. This one was done mostly by scientists and less by governments. There's more governmental participation here. They're very high quality, but they haven't turned out to lead to action yet. Well, then who are the defenders? That is, there are some people fighting on the other side, so to speak. In the case of the chlorofluorocarbons, there were only a few manufacturers, and the manufacturers of these packaged products, the aerosol spray cans, who opposed the regulations and who tried to say for at least 10 years that the science was wrong, it would never be correct, that we didn't know what we were talking about. But there weren't many of them. And because there were economic substitutes, the public was able to more or less reject these arguments, and they believed in universities, students and researchers at universities who did not have an economic stake in the problem. The public believed those people. In the case of the petroleum and mining interests in hydrocarbon fuels, there's an enormous amount of money involved, and people who are, I would say, intentionally rejecting the science because they have a strong economic interest or political interest. And then in places, certainly the United States, there are anti-government attitudes which do not want to accept regulations issued by the government, for example, or even if research involves government agencies now, it's not a dominant attitude, but there are parts of our society, I would say also in Australia and a couple of other countries, but certainly the United States, where there's an anti-government attitude which is making it much more difficult to deal with climate change than it was in the case of the ozone layer. And there are probably other reasons. So any of you who are interested, if you can think of other reasons why we're dealing with these issues differently, I would like to hear them. But I think I will stop there. I just tried to cover things briefly, and if we have some time for discussion, perhaps we can. Thank you. I have a couple of graphs of fossil fuel usage just to remind you of why this problem is not going away. But just one more graph. This is a graph of, what does it say? It's basically the millions of tons of carbon dioxide being released per year due to the combustion of natural gas, liquids like petroleum, solids, cement, and gas flaring, showing the enormous rate of rise. And you can get a per capita answer by dividing by the world population, which also continues to rise. So the problem with fossil fuel combustion is not going away because we need the stuff and because we haven't found good substitutes yet, and we're not being very efficient. Okay?
We'll have, how long? Around 20 minutes for question and answers. Anyone? Any question? Yes, Professor Jiang.
I raised 3 times my hands yesterday during your talk, but chance never came to me. So I raised
you
my
got a
hand.
good friend here now.
Right, yes. I'm a geologist, and you know that some geologists study paleoclimatic change. And you briefly mentioned that in the past, in the geological past, the temperature variation has been documented. And I think it's still a very serious scientific issue. That is, the increase of the temperature is entirely due to the greenhouse gases, or the greenhouse gases only contribute part of this cause. I understand that I'm not a climatologist or paleoclimatologist, but I'm interested in this issue. And I know some papers in JGR or GRL, they published that the correlation between the temperature variation and the CO2 is not really perfect. And some scientists they try to correlate temperature increase with solar irradiance, and they found that the match is much better. And in the geological past, this climate, the temperature change, the variation is, the amplitude is very big, and sometimes greater than 8 or 10 degrees. And this period was before the arrival of Homo sapiens. So apparently some increases has nothing to do with CO2. So I would like to hear your opinion about this. Thank you.
Is it turned on? Well, as I said earlier, not all climate change is due to human activity, and I was thinking about the paleo examples. But it is not logical to say that because there have been changes before humans, that the current changes are not due to humans. That is not logical. I think the true answer here is we have everything going on simultaneously. And the evidence shows that the contemporary climate change, the signal of human activity, has emerged out of the natural noise. And the paleo, I certainly agree with you on the importance of paleoanalyses, however, because there are aspects of geological climate change that we do not understand. For example, what triggers an ice age? How do you start an ice age? And then what stops it? As far as I know, the computational models have not been able to answer those questions. There are some missing factors that we do not understand. But the time period, of course, in geological history is so long that the pace, the rate of the changes that we're seeing now are faster. And I think that's a cause for lots of the concern now. We must work together on these issues to understand it, that's for sure. However, the French results, which correlated temperatures over geologic scales with a geomagnetic index, they are demonstrably wrong. I don't know why people are still talking about them.
Any other? Yeah, the lady on the fourth row.
I'm an English teacher at an elementary school, and I would like to ask, could you suggest us that what we can do in daily life to protect the ozone layer? And the second question is that I used to study in Australia before, and my Australian friend mentioned that the chemical in sunscreen actually cause more harm to human skin than the radiation from the sun. So I was thinking that you mentioned the loss of ozone layer is the cause of skin cancer. So I wonder which one is cause more damage.
May I ask you first, what kind of damage have you heard about to skin? What kind of damage are you referring to?
I'm not really sure, but it's just they.
It might cause an irritation, I'm not sure. It depends on what's in the chemical. But in terms of protecting against ultraviolet light, they're very effective. The misuse can cause problems if people believe that if they put the sun repellent on and then go swimming, the material does get washed off. And some of the labeling is inaccurate. It will say water repellent when it's not really. But other than that inadvertent danger, I don't know of any. So what can we do today to protect against the ozone layer damage? It's basically been solved by technology and the Montreal Protocol. The chemicals that we use today for refrigerants are really much safer because they don't have any chlorine in them. So as far as we know, the refrigerant fluids we're using today and the aerosol spray propellants are safe. And that's a success story. Very fortunate.
Any other question? Any other question? Where? Oh, yes.
Thank you for your excellent presentation, especially the comparison between the ozone depletion and the climate change. And then could you elaborate the implication? I mean, can we learn something from the Montreal Protocol, for the Kyoto Protocol, or at this moment the mitigation is of no use? We should follow the adaptation strategy. I mean, could you elaborate on this kind of the lessons? I mean, we can learn from your experience. Thank you.
I think the people who designed the Montreal Protocol made a very important contribution by permitting a series of reviews and demanding that the entire base of information had to be reviewed after a few years. And as it turned out, in the case of the ozone layer, the evidence became stronger and stronger and stronger that there was going to be damage. But it allowed the nations with different interests to move together. And instead of making one final decision and sticking to it forever, this series of adjustments I think has turned out to be very valuable. And with climate change, I think it's a very sensible approach, because we will get some surprises out of climate change, I think. We do not know exactly where we are headed in terms of precipitation and the stability of the seasons and all kinds of things. So if I could take one lesson out of the Montreal Protocol, it would be that any future agreements about climate change should permit continuing argument, for example, over economic grounds, or, for example, what if some large natural climate change happens simultaneously that could reverse the events? So we start with our best available information, which I am saying right now shows that humans are causing the climate change, and it's going to become much more pronounced. But if we have some agreements, we should allow for adjustments to be made every few years. I think that makes sense.
Frank.
Yeah, wonderful presentation again. One thing that struck me during your presentation is the difference in the company's reactions in some sense. I don't ever remember any company trying to label the scientists working on ozone problem as being in cahoots, trying to perpetrate a hoax, such as we see today. Or any company today accepting a killer argument, right? That DuPont, you said, well, if you find these two things together, this proves it. I don't think any oil company or gas company would accept that today. They would deny it to the end. So in some sense, we are in a very different game. And perhaps, we got to do something. Maybe we should just ignore these people, and say, there's nothing that they will accept, and that we have to go ahead and try to find solutions.
Well, there were certainly some attacks on the credibility of scientists back in the 70s. I remember giving a seminar at the University of Chicago in late 1974, early 1975, where a gentleman stood up in the audience, and he was an aerosol spray can manufacturer. And he said, "You are more of a threat to our country than the worst saboteurs were in the Second World War." But it wasn't as widespread.
Any other questions? Yes. Yes.
Actually, my question is a bit irrelevant to the climate issue, but more personal. I was wondering why you decided to change from electrical engineering to climate studies, because it's a bit like quite different. And have you faced any difficulties during the process? Or?
None. Never.
No?
Never. No, I think that's an interesting question from the point of view of a lot of students. When you go to a university and even graduate school, many people think that that course of study will determine the rest of your life, that you will be on a certain track. Whatever your degree, whatever the name of the degree was, that's what you will do for the rest of your life. And it's not true. It really isn't. And it's a source of fear for a lot of students that they really have to commit to that one track and do that along the way. And many people do. For example, some little children want to be a medical doctor, and they succeed in the rest of their life, they become a medical doctor. That's good. But there are other people who develop other interests or see other opportunities, and I think it's important to realize that what you learn in a university can serve you in so many different careers, public service, private, and I just kept going until I found something I was interested in. But I mean, I could tell you the detailed steps that happened along the way. But the gist of it was I didn't feel constrained by the fact that I had a degree in one subject or another. I just looked for things that were interesting.
Further, the one in black. Back, yes.
Good afternoon. I'm a student major in chemistry, and I'm quite curious about what is the main difference between being a scientist and being a president of National Academy of Science of the United States.
Well, certainly what I do in a normal day is different in the two cases. Being a scientist, usually one is investigating something very directly in the laboratory or in a field or reading data. As president of an academy, I have a wider variety of duties. Sometimes I simply mediate disputes between people. Other times I try to understand how a result from one field of science or interest will affect someone else, or what are the medical implications of something being discovered in physics or chemical engineering or something like this. But the scientific background is very useful. In fact, I think the mathematical background that you have maybe from the time you were 15 years old through the university, the mathematical background is maybe the most important because it allows you to move into almost anything. So I see more similarities than I do differences.
Gentleman, fourth row, yeah.
Dr. Cicerone. Wait. The first question is, what kind of solutions are better for us in our generation? The second question is how to balance the economic advance and the environmental justice. Thank you.
Well, I think the solutions that we have available right now might not last forever, but we have to get started. I think energy efficiency is an extremely good one to start with, that we should try to make our use of energy more efficient, like insulation in buildings and light bulbs that are more efficient in producing light. And I know these sound like small things, but we can make big gains, and there's easy results available if we just commit to it and demand better products from large manufacturers, like automobiles that are more efficient, batteries that are more efficient, lighting, heating and cooling, and so forth. And then when we exhaust that potential value, we have to move on to other solutions like implementing more renewable energy, because there is growing demand for energy that cannot be satisfied completely by efficiency. Although we can gain about 30% in our energy capacity just through efficiency in most places. But eventually, due to growing human population, we need more energy that I think renewable and perhaps safe nuclear power has to be developed. About making trade-offs between, let's say, environmental justice and economics, I think people agree, and there's a lot of motivation. So I think as in the next 10 years, 20 years, there's going to be tremendous gain. Better education, making available a better economy to very poor people, the lowest 2 billion people, and so forth in terms of economy. There's a lot of agreement that their medical needs, their needs for clean water have to be matched. And I think the technology is available, and some of it can be supported through natural economics. I think we do need good governments, and all of us can help there by demanding more intelligent participation and knowledge-based decisions from our governments. So we need all of these things, but they're not impossible. But you will not solve the problem once. You have to continue to solve the next set of problems. I think that's the way human existence works. The challenges will change with every generation.
One more question? Yeah.
Good afternoon. As doctor, you have said, people's future work may not have that close relevant to what they have learned in university. So my question is, what is the ultimate goal we have to pursue, or what kind of altitude we should learn in university? Thank you.
I think you should answer that question. What is your ultimate goal? I mean, I could give you my list, but it's no better than your list.
I'm a freshman, but I have interest in scientific research. I have wanted to be a professor, but although I'm still a freshman.
Well, I think there's a set of very inspiring goals that surround teaching and research, certainly. I mean, what humans have been able to attain in using science only 300 or 400 years is absolutely spectacular. And what remains to be learned about the human brain and its capacities, with human diseases, with how to permit other forms of life to prosper, these are really inspiring goals that I think education is it's absolutely essential. But whether that leads you into biomedical engineering or physics or mathematics, I don't know, but the overall set of goals is very inspiring. You can say that respect for life might be an overwhelming goal, or improving the human condition might be another goal, preserving forests, whatever. But I think education is at the it's absolutely essential. We cannot do anything without education.
Okay, I think time is up, and please join me to give the Professor of Cicerone a big hand, please. And thank you for your attendance. Thank you.